Okay, just gonna go over your review for your quiz, Unit 6, quiz number 1. So this was all on properties of exponents and then some exponential functions as well. So this review is just like the skills that you need to be successful on that quiz. So first, simplifying expressions and then making sure our answers only have positive exponents. So on the first one here, when we're simplifying something like this, we're just looking for common factors between numerator and denominator, and there aren't any common factors. The only thing that we can simplify is this y to the negative 3. So whenever something has a negative exponent, it's you can always move it to the other side of the fraction to make it positive. And so we would just move this up, just the y. So the 2 stays there, and then we have x to the third left on the bottom, and y to the third comes to the top. And by switching sides of that fraction bar, it becomes positive. All right. The next one, just again, some more properties of exponents. So if I'm going to simplify that, I know anything to the power of 0 is equal to 1. So this n to the 0 right here is really just multiplying by 1. And then the p to the negative 4th, well, same idea. We have to move that to the bottom. So I'm going to turn this into a fraction. M to the third will stay put right on the top, and then p to the 4th on the bottom. So that negative exponent moves it to the bottom and it becomes positive. And on the last one, again, it's a fraction. And so we're just looking for common factors between the numerator and denominator. So we'll just go straight across. So the first one, 28 and 4, 28 is divisible by 4, actually. 4 goes into 28 7 times, and 4 goes into itself once. So I know we're just going to have a 7 there. Looking at the a's, we have a to the 12th divided by a. So anytime you have just a variable without an exponent, remember it kind of has like this little power of 1. And when you divide powers with the same base, you subtract their exponents. And so a to the 12th on top, take away 1 because of the a on the bottom. And so this will make this be a to the 11th. 12 minus 1 is 11. And then same idea with the b's. The b to the 5th divided by the b to the 3rd is b to the 2nd, because 5 minus 3 is 2. So the final answer is 7, a to the 11th, b to the 2nd. All right. The next one here, make a table of values for the function f of x equals 3 times 2 to the x using the input values of 0 to 8. So the input values, those are the x's. So I'm going to number the x from 0 to 8. And then if I just read the equation, it's telling me the initial value is 3. So this is a 3. And then it's just multiplying by 2 over and over and over. So 3 times 2 is 6. 6 times 2 is 12. 12 times 2 is 24. 24 times 2 is 48. 48 times 2 is 96. 96 times 2 is 192. Oh, this is getting hard. And then 192 times 2, I'm just going to just check my work real quick here because I'm starting to doubt myself. So let's see here. Okay, so 384. And then 384 times 2 is 768. Okay, so one way I could do that is just like starting with 3 and then multiplying by 2. Another thing that I taught you how to do is to actually put an equation into your y equals. Oops, looks like I have some in there already. I'll just get rid of them. Okay, so you could put that original 3 times 2 to the power of x into the calculator, and then look at it on a table. And so my table is starting at 0. So I have those same values there. And then just checking for 7, and then for 7 here, and then for 8. So it matches up. So again, that was just putting the equation into y equals, and then second graph to look at the table. All right, the next one, describe the similarities and differences between each set of functions. And so when I'm looking at these sets of functions here, I'm thinking about, for that first set, the second set, and the third set, it's kind of all the same. They're all like starting at the same initial value, right? So, so that's when x is 0, y is 10 for both of these, right? However, the growth factor is different, and these are both growing. So the growth factor here is 1.3, and the growth factor here is 1.7. So I'm going to say they're both exponential growth, but I don't know why I put a W there. I think I was thinking of growth. But if I was to look at them on a graph, they're both going to start at 10 and increase exponentially. But this one would be G and this one would be F. And that's because 1.7 is a larger growth rate than 1.3. Okay. So that's how I would know the difference between them. And I'm just going to stick with making a graph for each of these to explain it. I think that would actually be very helpful. These two functions both start at 90. So they'd have a point here at 90 on the y-axis. They're both showing exponential decay. So one's going to decay. They're both going to decay. But which one is which? Well, which one is getting smaller faster? It has like a larger decay rate, I guess you could say. So this would be F down here, and this would be G, okay? Because more is taken away. Wait just a second. It's the other way around. This would be F, because F has 50% left each time, and this would be G, because G has 30% left each time. So it's the opposite of what you would think, I guess, a little bit. So this one's going to drop faster because it has a smaller decay factor. Okay, it's closer to 0. All right, and then the last one, well, they both start at 100. But again, they're growing at different rates. So one is doubling and one is like 2.1. So the one with the larger growth rate would be the one that gets larger faster. And then so that's G. And then this one would be F. Okay. Next, here, it says write 3 different equations that could describe the exponential function in this graph. So what I know about this function is it has an initial value of 3. And I also know that if it's showing exponential growth. So I know 2 things. I know that A is equal to 3. So if we're thinking about y equals A times B to the x in that model, I know that A is equal to 3 because that's where it's starting, right here on the y-axis. I also know that B is greater than 1 because this is growth. This is increasing, so the factor has to be greater than 1. there isn't a scale or any numbering, so I can't actually figure out what B is, but that's why it says could. So maybe I'd say y equals 3 times 1.4 to the x. That would be okay because 1.4 is more than 1. Maybe I could say y equals 3 times 1.2 to the x. Also okay. This just has to be any value larger than 1. You have to come up with 3 of them. So there's 2. You can come up with some more on your own as long as you have your a value is 3 and your b value is greater than 1. Okay, next, write a function rule or a function to describe the values in the table. All right, so again, in that model, y equals a times b to the x. We need to know the initial value. This one is nicely given to us. This tells me that a is equal to 5 because that's what the value of the function is when x is 0. So we got that part done. If I'm looking at this table, it appears to just be multiplying by 3 each time. And you can always, if you kind of make that as your guess, you could always go, is it multiplying by 3 each time? I mean, I know 5 times 3 is 15. Okay, so yes. And then I don't know, what's 15 times 3? Oh, look, it's 45, just like what it says in the table. And then that times 3 again is 135. So it looks like our constant multiplier is 3. So since it's times 3 each time here, that tells me the b value is 3. So maybe f of x equals initial value times the constant multiplier to the x. All right. And then we have some story problems. Compare and contrast the functions that model the growth of a mold population. So, and I gave you some specific things to talk about. So for the first population, m of x equals 500 times 2 to the t over 4. So the exponent is t divided by 4. And then n of x equals 500 times 2 to the 4 times t. Okay, to the 4t, 4 times t. So initial population, they're the same. They are both 500. Which one is growing faster? Well, let's think about that. So time is is what t represents. T represents time. So if they both have both of those exponents have a base of 2, but then there's some work done to the exponent. So dividing by 4 or multiplying by 4 is going to give you a larger answer. So which one's growing faster? N of x. Because I'd say there's, as time goes on, 4 times t is more than 4 divided by t. Okay, so for larger and larger values of t, when you multiply by 4, you're going to have more than dividing by, dividing by 4. What is the daily growth factor? So you might go, it's 2. It's not 2. Because those aren't just t as the exponent. Neither one has a t as the exponent. So what happens in this one here is it doubles every 4, whatever the unit of time is. Let's say it's days, every 4 days. Okay, that's what it means when it's dividing by the 4. It takes 4 days to double, whereas multiplying by the 4 means it doubles 4 times each day. Okay, so in 2 days, the second population would have doubled 8 times. Okay, so the daily growth factor isn't 2 because it's happening more often. So what we want to do is break that exponent apart like we've done on other problems. So if we take, for example, 2 to the t divided by 4, that's equal to 2 to the 1/4 times t, right? Because t divided by 4 and 1/4 times t, those are the same thing. Now, when you multiply exponents, you can do the same thing by power to a power. So I can just say, oh, this is the same thing as 2 to the 1/4 to the t. And that allows me to figure out the daily growth factor on my handy dandy calculator. 2 to the 1/4 is about 1.1. I'll do 1.189. So this is 1.189 to the t. Okay, so the growth factor, the daily growth factor for function m is 1.189. I'm going to just put it up here. 1.189 for the daily growth factor. Okay, for the second one, 200 or 500 times 2 to the 4t, we can skip these steps. We can just kind of get from here to here. So we have 2 to the 4t, and 4 and t are multiplying. So this is equal to 2 to the 4th to the t, which makes sense because it's doubling 4 times every day. 2 to the 4th is 2, 4, 8, 16. So this is equal to 16 to the t. So the daily growth factor for this population, for that species or whatever, population of mold is 16. Yikes, that's a lot of mold. All right. Okay, so that's the daily growth factor here. I'm just going to label that. Okay, how long does it take to double? So I can just figure that out by looking at the exponent. So since the base is 2, this 2 to the t divided by 4. So what that means is that for m of x, it doubles every 4 days. Okay. And then for n of x, I already wrote this out, it doubles 4 times each day. So if it doubles 4 times each day, and a day is 24 hours, then it takes 6 hours, right? 24 divided by the 4 times that it doubles. So every 6 hours. So n of x doubles every 6 hours. Okay, again, this means 4 times in a day. And a day is 24 hours. 24 divided by 4 equals 6. So that's how I got 6 hours. 24 divided by 4 is equal to 6. Okay, last problem. Population of 1,200 termites, yikes, found in the foundation of a house. 5 days later, the population had grown to 22,700. So this is similar to the problem we did in class. Oh my gosh, I cannot remember. Oh, about the giant snail invasion. It's nice because we do know the initial amount. So what we know is, let's say X, and then I'm going to use maybe T for termites. We know initially there were 1,200 termites, and then 5 days later, 22,700. Okay? And so I know that this gets multiplied 5 times to get that. So 1,200 times some factor to the 5th is equal to 22,700. Okay, so again, we did this in class the other day. So the first thing I'm going to do is just divide 22,700 divided by 1,200. 22,700 divided by 1,200 is a long decimal. I'm just going to have to round it. It's fine. So that tells me that b to the fifth is equal to about 18.92. This is a 992. Okay, so I know the initial amount. I don't know the value of b. I don't know what the growth rate is or the growth factor, but I can figure it out now by raising both sides of the equation to the 1/5. Since this is b to the fifth, I can raise both sides of the equation to the 1/5. And that tells me, let's see here, 18.92 to the 1/5 is about 1.8. Okay, so I'll write that down. So after doing this, I get that b is about 1.8. So I know the a value, I know the b value. We can write an equation. So the equation, let's say t of x for termites, equal to the initial amount, 1,200, times the growth factor, which is approximately 1.8, to the x. Okay. And then finally, if left untreated, what will the termite population be in 2 weeks? So our initial unit, this is in days. And so in 2 weeks, we're going to use an x value of 14 because there will be 14 days in 2 weeks. So to answer this question, you just find the answer to 1,200 times 1.8 to the 14th. And let's see what it is. 1,200 times 1.8 to the 14th is a whole lot of termites, like over 4 million. 4,497,760. Woo! 4,497,760 termites. That's a lot of bugs. All right, if left untreated. Okay, so this is just a selection of skills that you need to have mastered to be successful on the quiz. I'm sure you're going to do a great job. I hope the video was helpful. All right.